One of the basic goals of physics is to describe something that happens with math and pictures. Let's take a simple example. We have a picture standing on top of a cliff, and the cliff is of height h, and she throws the ball perfectly horizontally with a speed v0. The ball leaves her hand directly above the cliff edge at a height above the cliff of y0. How do you describe the position of the ball as a function of time? Well, the first step is to choose the origin of your coordinate system. There are many possible choices. One good point would be the position where the ball leaves her hand. The reason for choosing this is that once it leaves her hand, she's no longer affecting the ball, and the motion is relatively simple. You could also choose the top of the cliff, and this would be a good choice too, because again, the x equals 0 point is right where the ball leaves her hand. Or we could even choose the ground, because maybe we're interested in what's happening when it hits the ground or where it hits the ground. All of these are good choices. We also have to choose when the time is equal to 0. Not only the position is equal to 0, but when is time equal to 0. And a good choice for the time equal to 0 is the moment when she releases the ball. Because again, once she releases it, she's not affecting it. So how do you describe the position of the ball as a function of time? Well, our third step is to use some physics knowledge. The motions in the x and y direction are independent of each other, so we can deal with them one at a time. A general position u of t, this would be x, y, or z, is a function of time, when there's a constant acceleration in the u direction, a sub u, is given by this formula. So u as a function of time is equal to the initial u position, u sub naught, plus the initial velocity in the u direction, that's v sub u comma 0, times time, plus 1/2 times the acceleration in the u direction, times t squared. There's no acceleration in the x direction, but there is an initial velocity in the x direction, and there's no initial position in the x direction. So x of t is very simple. There's no first term, there is a second term, which is v0, the speed with which she's throwing it, times time, and there's no acceleration. So it's very simple. For the y term, we have that the y of t has an initial position, y0 plus h. That's how far you are from the origin up to where the ball is released in the y direction. And we also have there's no initial velocity in the y direction, so that term is gone, but there is an acceleration. And the acceleration is minus g, and the g is the little g for the acceleration from gravity, 9.8 meters per second. So it's minus 1/2 g/t squared. Okay, now let's make some pictures. So for the x of t, it's a straight line plot, and the slope is v0, so the velocity. Very straightforward. The y of t is going to be a parabola. It starts at the initial position, y0 plus h, and decreases, so it's a downward facing parabola, or at least half of one. And it continues going down until it hits the ground when y is equal to 0 at some time. So the question is, when does it hit the ground? Or at least that's one of the questions. Well, that's when y is equal to 0. So we can plug in 0 for y of t and solve for t. And that's fairly straightforward algebra. You move the variables around and solve for t, and you get this value. T is equal to the square root of 2 times the quantity of the initial height, y0 plus h, divided by g. Where does it hit the ground? Well, you just plug in this time into our x of t formula, and that's our final x position when it hits the ground, and you're done. Okay, now it's your turn. Give it a try in the next problems.